Hi, it's time for another math easy solution. Time to discuss further into trigonometric integrals and now look at some guidelines for solving basically integrals of sine x, cos x when you have different powers. Basically, to summarize on the examples I covered in my earlier examples, the following guidelines help in evaluating integrals of the form. You have something like this: sine to the power of m of x times by cos power of n of x dx. Yeah, where basically m and n are greater than or equal to 0 and are integers. For example, it could be 0, 1, 2, 3, etc. and so on. So basically this is the strategy. If the power of cosine is odd, for example, n equals nk plus 1, where basically k is also an integer that's greater than or equal to 0, so k equals either 0, 1, 2, etc. So whenever you put anything here, if you put a 1 here, you're going to have 1, or no, if you put a 0, n is going to be 1. If you put a 1, 2 times 1 plus 1, that's just 3. So you always get an odd number here. So if power of cosine is odd, so the strategy is to save one cosine factor and use cos squared x equals to 1 minus sine squared x. Use this identity to express the remaining factors in terms of sine. So for example, if you had right here, you had sine the power of m of x times it by cosine right here 2k plus 1 of x dx. Right here, this one we would, so yeah, we would save one sine factor and then we would write we would save one cosine factor, so we'd write sine m x, and now we would save one of these, so times it by, well, and to do that we would first of all we would break this up, so we would have 2k x and then times it by cosine of x dx. So now we have separated this by itself, and also we would actually rewrite this in an easier format. So we would take this k out of the power, so we'll have cos squared x, and then we put the power of k. Yeah, so this is the same thing as having cos to the power of 2k of x. So now we have this part, and we do this so we could apply this formula right there. So this would equal to sine m of x times by 1 minus sine squared of x power of k cos x dx. Yeah, and then basically we would substitute u equals sine of x because du, or the differential, is going to be cos x dx. So now that we've had only one cosine factor, this du replaces this completely, and now when we plug in this u, we're going to be dealing with just u, or just sine of x right there. So we could deal with the substitution there. Yeah, and in fact we will get basically this top part here is going to equal to integral from this is going to be u m of x. Actually no, the x is gone. So u to the m 1 minus u squared power of k, and then this is going to be du. And then we would just expand this out and solve the integral, and then plug back the sine inside, and that's pretty straightforward. Yeah, now the second case is if the power of sine is odd. For example, m is equal to 2k plus 1, so then we would just save one sine factor and use this function, or this identity, sine squared x equals 1 minus cos squared x. So basically we just do an opposite of this first step to express the remaining factors in terms of cosine. So for example, if you had sine, then we'll have a not an m, sine 2k plus 1 of x times by cos n of x dx. We would do the exact same thing as we did before, so separate this. So we'll have a sine squared of x to the power of k times by cos n of x, and then put the sine here at the end. So sine x dx. Yeah, and basically from here we would apply this trig identity, so we'll have a 1 minus cos squared of x power of k times by cos n of x sine x dx. Yeah, and then once again we would substitute now. We'll have it u equals cos of x, because du is going to equal to, well, negative sine x dx, which would replace this part right there. So then this part would equal to integral of 1 minus u squared power of k times by un, and now we'll have this sine x dx. It's going to be du, and then we'll just have a negative sign on this whole function. And then we would just evaluate this integral and then substitute this back inside. Now if the powers of both sine and cosine are odd, so if both of them are odd, then either steps A or B can be used, so it doesn't matter which one you pick. And now the last guideline step is basically if the powers of both sine and cosine are even, then we would use the half angle identities, this one right here, sine squared of x equals to 1/2 of 1 minus cos 2 of x, and this one we could use as well, cos squared equals to 1/2 1 plus cos 2 of x. And this basically makes, if you have a squared, it basically reduces the power from the 2 to having no power. And also this is called half angle because this angle x is half of this angle 2x. And now also it's sometimes helpful to use this identity, is this one right here, sine of 2x is equal to 2 sine x cos of x, because if you ever are dealing with sine x cos x, you could rearrange this and this will be sine x cos x equals 2 1/2 sine 2 of x. So basically this allows you to reduce one of the cos x's by removing one of these out of there and using this identity. And yeah, these are basically the steps in solving sine times cos when you have different powers of both of them. And yeah, and basically make sure to use these make sure to understand these guidelines and also review these as well as my earlier examples, which basically this helps to solve the earlier examples I did on integrals involving sine and cos. Anyways, that's all for today. Hopefully you learned from this video, and like always, you could download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.